Open up the door, it's Dave!
Who?
Dave! D-A-V-E!
Dave?
Right, man, Dave.
Dave's not here.
It's wintertime in most of the country, and most of the northern hemisphere for that matter. I happen to live in Florida where wintertime brings temperatures like in the 70s, so I'm wearing short sleeves. Not to gloat, but I don't see the same problems that some people see with their cars when they're driving in cold weather. There was a story about 2 weeks ago about a group of people that had an incident in Chicago where the temperatures dropped so low and everyone was trying to use the superchargers and the cars wouldn't charge, and there was a whole bunch of things that happened. And what we were missing in that story was the context of it, that people didn't realize that preconditioning the battery is really, really important. And in fact, in the Tesla manual, it reminds you that preconditioning is kind of a prerequisite. But most people don't think about that. They think about driving their cars, they just plug in, they go on their way. And until batteries get to the point where they're solid state and they don't have to have the same problems with the cold weather, this is going to be a problem. And this goes along with the whole idea of there being problems with not enough charging stations and having this understanding of how charging works. I've never had a problem with my car in terms of charging, in terms of going somewhere, getting a charge. When it's really hot out here, the fans have to turn on to cool the battery in very much the same way that they do to warm up the battery. But it's a little different because it can take a charge when it's hot, it's not a problem. When it's cold, as I showed you in a video last year, the cold will actually bring the charging level down, and you'll spend most of your time just warming the battery before you start charging. So it's really important to do preconditioning, especially before you do supercharging. So that's one of those things that you really just have to understand. Now, I thought it would be interesting to kind of do a little experiment here to try to figure out what happens when you take a battery that's a rechargeable battery and you freeze it. What happens to the battery and how does it charge, and how does the battery get affected by this? We know the science behind it, but let's actually see it in action. Hold up for 1 second before I get into it. I wanted to make one quick disclaimer. I'm going to use an old voltmeter. I don't have the ability to measure amps on that voltmeter, so I'm going to use Ohm's law to do that. And the voltmeter itself may be a little bit inaccurate. When you see the readings on it, you may go, what? But just keep in mind, this is really illustrative. I just want to share with you how this works so you have a sense of how it all comes together and why it matters when the battery freezes. Now, when I started with this experiment, I wanted to use an old Radio Shack voltmeter I had that was a digital display and worked fairly well until recently. As you may notice here, it gets a little annoying. Yeah, the voltmeter stopped working completely, but I guess the fact that it's 30 years old and provided a lot of service to me, I can accept that. So I went ahead and moved on and went back to an analog voltmeter that I've had for more than 40 years, and that seems to work pretty well. It's also a Radio Shack model. Now, what I decided to do was take a battery that's an N-loop battery. These N-loop batteries are nickel metal hydride chemistry batteries. So they're similar to what you have in a car, and they're made by Panasonic, which is similar to what you have in a car too. So I'm going to take this battery that's mostly charged, and I'm going to hook it up to my voltmeter just to see what it looks like today. At room temperature, just taking it out and using it. So I'm going to go ahead and attach both ends to the voltmeter, and what I see is that I'm going to get voltage on it, and then I'm going to measure the ohms that are in it, and that way I can get to the amperage, because this voltmeter doesn't give you amperage. So when I put it on the voltmeter, I see that it's about 1.25 volts that are in it currently. And when I hook it up to the ohm meter, I see that it's a little below zero. Now, I know that that's not quite zero, and I know this doesn't read quite right, so I'm going to call it like 0.1. Anyway, I'm going to go ahead and now take the battery, put it in the freezer, and freeze it for a couple of hours and see what happens. So I'm going to close it up, and about 3 hours later, I take it out, and I'm going to redo the measurement just to see what it looks like. Now, I'm trying to be fairly careful by touching it with a towel instead of my warm hands, just so it stays cold while I go to measure it. Now, what I notice is when I look at the voltage, it actually dropped a little bit. It's at about 1.1 volts. And when I measure the ohms, I see that they've gone to about 3. So both have changed because of the freezing. So now let's talk about Ohm's law. We can calculate the relationship between voltage, current, and resistance in an electrical circuit. Since we couldn't get the amps directly from the voltmeter, we can actually calculate them in that case, and let's do that now. But first, let's talk about the definitions of these things. First, we have the current. It's measured in amperes, and we're going to represent that with an I. We've got V, which is the voltage, and we measure that in volts. And then we've got the resistance, which is measured in ohms, and that's the R value. So let's go ahead and do the calculation here. We know that I equals V over R. That's the relationship. So if we do the calculation based on what we knew at room temperature, we know that it was 1.25 volts and about 0.1 of an R, which would be about 12.5 amps that we're able to get out of the battery. On the other hand, when it's frozen, it's 1.1 volts and an R value of 3 ohms, which would be about 0.367 amps, which means that you're not getting as much current out of the battery, which is exactly what you would expect when the battery is frozen. And this is the nature of the problem where you had the cars in Chicago that were unable to charge. Preconditioning the battery solves that problem. As I noted at the beginning of the video, this is really for illustrative purposes. This is just to show you why preconditioning the battery matters, because batteries, when they get frozen, actually have a different chemistry and they have a bigger resistance in them. Sure, what I showed here by using my voltmeter is probably not that accurate. It's probably off by a bit, and some of you may even question why I used it, but it really was just there to illustrate the principle that when you freeze the battery, it makes a difference. And that's it. Now, isn't that kind of cool, the way we just did that? We looked at this battery and we understand that the battery will not accept a charge when it's frozen like this. Now you let it warm up a little bit. If I had put a hairdryer on it or just let it sit at room temperature for a little while, it would have warmed enough where it would have gone back to a normal state and then used that. So what's happening is the battery just actually freezes and it can't accept a charge. So until we overcome that, this is going to be a continual problem for charging. And I just wanted to kind of share that with you so you had an understanding of what it's all about.
What's your point, David?